Hello everyone. So you probably have watched Eric O's video about a crankcase position sensor that looks good on the oscilloscope, but results in the car throwing off some misfire code. And Eric was kind enough to share the Pico files with us, so we can download them from the Google Drive and then go take a look what's going on there. So let's do just that. Okay, so we are going to start a Picoscope. This will be the one for Linux, but any version would work just fine for us. So I will not use the demo device. Instead, I'm going to load the new sensor at idle. Okay, we don't need the nodes, but what I'm going to do right now, well, first of all, we probably are going to use split screen. We will run several Picoscopes so that we can take a look at the waveforms together. So I use the half of the screen. I'm going to lower down this so that we have a more compact form, and what I'm going to do now is zoom into this region where the blue trace is high, and I will try to do that so that I actually have it all on the screen. Oh, like this. Okay, so we have the three sections of 4 signals. The blue trace, the high value, is spanning the whole screen, and we will use the cursors to measure the distance between the two sides of the screen, and we see that it's 86.22 milliseconds. Okay, that's good. What we're gonna do now is to use measurements for channel B, and we will try to use high pulse width, but we won't do it on whole trace. We'll use between the rulers. So this is actually important because we only want to figure out whether the signal is high only on this particular screen. And the same thing we will do for the duty cycle, channel B duty cycle between the rulers. We don't really want to use the duty cycle for the whole trace because we actually don't know how many pulses actually got into the trace. There could be more, could be less, but when we are looking at this section where the blue trace is high, we know that there will be 3 multiplied by 4, 12 pulses inside it. So the measurement will be precise. So we have basically everything we need to know to compare it to the idle with the old sensor. Okay, so I did the same for the idle for the old sensor, and everything is lined up perfectly, and so we can do the direct comparison over here. And just by looking at it, we see that the signals are in the proper places, so basically just going down just nicely, but the width is different, and this is something that we will focus on. We have to figure out by how much this width is bigger for the old sensor than for the new one. So we can use the high pulse width over here and compare them, but we have to be careful about that because we have a slightly different length for the this blue trace duration. So in one case it's 86.22 milliseconds, and in the other it's 85.6, which are pretty close here. So we can still just do the comparison. We can see that these values are about 40% different. We can also see that on the duty cycle, that the duty cycle for the new sensor is significantly lower than the duty cycle for the old sensor. So even at idle, we can see that that sensor is different. It doesn't have the same pulse width. This pulse width is bigger. Can it be because the sensor somehow got too close to the magnetic wheel or something? Or maybe some electronics in the sensor became too sensitive? I don't know. This is something that can be explored, but I guess it's easier to put in the new sensor and not worry about anything like that. Another thing is that, well, the software that tries to interpret these sensor signals, maybe it's not robust enough for the pulse width differences. It looks like it would be quite possible to write a software in the PCM to account for a different pulse width if this is, a regular pattern. But it looks like whatever the algorithm is in the PCM, it accounts only correctly for this pulse width, and when the pulse width is somewhat bigger, it starts giving out erroneous results. And the same thing we can do for the 2500 RPM. So let me just minimize those and bring up the ones for the 2500 RPMs. Here we go. So here we have substantial differences between the blue trace pulse width, because it's 22 milliseconds versus 25.8. That's because it's very hard to keep the engine exactly at 2500 RPMs. So we have to be careful when comparing these numbers for the high pulse widths and for one sensor and the other. So let's just try to do that using, let's say, a spreadsheet calculator. So what we need to do for the first case, we have 134 just excuse me, 134 microseconds for the pulse width, and the total is 22.16 milliseconds. So why don't we just divide one by another and see what happens. So we get the value around 6. Now we will do exactly the same thing for the old sensor. So we would have to take 212.1 and divide by 25.84. So that would be 8.2. And how much this is different we have to divide 8.2 by approximately 6, and that would be about 40% difference. So yeah, it's 40% different, pretty much regardless whether you try it at the idle or you try it at the 2500 RPM. It looks like the positions of the pulses are matching. They are not really floating around or anything, but the pulse widths are different, and unless you know how big this pulse width should be, you cannot really tell whether the sensor is good or not. And this is one of the complications in diagnosing this issue. And well, I guess it really helps to have the prior experience about this sensor in order to make the right call.